Hello, how we doing? Ionizing radiation and nuclear reactions today. Oh my god, I can't write with my pen. It's sad. Because I want to erase. Okay. Ionizing radiation and nuclear reaction reactions. Name it. Everything's bad today. Okay, name it one. Yeah, because this will be separated into like two videos because it's a big topic. Yeah. Okay. So I'll start on the subtopic. Yeah, kind of nuclei nuclei. Oh my gosh, my bad. Nuclei and radiation. Yeah. And I'll do my first question, and it'll be on. It says plutonium plutonium 239 is a major waste product of nuclear reactions. Decays and it decays by alpha emission. Its daughter also alpha decays, leaving a residue nucleus that beta decays. Write the nuclear decay equation associated with each decay. So start with this, yeah. So we'll just say we'll actually just write the actual name of the periodic table because it's too long. No one's writing that. So plutonium is Pu, and it is 94. So we write the mass first, 239, 90, 94, yeah, 94. And undergoes alpha decay, so it becomes something plus alpha particle. Alpha particle, yeah, alpha particle. So alpha particle is 4, 2. So this subtract 4 is 2, 3, 5, and 94 subtract 2 is 92. Oh my god, 92. Let's see what that is. 92 is uranium. So you sorry, uranium. That's it for the first reaction. Oh my god. Okay. First reaction. Second reaction is we start off from uranium because that's its daughter particle thing. Okay. Uranium and it undergoes alpha decay as well. So it's 4, 2 again. And that becomes 231. And that becomes 90. 90 is thorium. Thorium. And the third one, that's it for the uranium one, because simple. And then the next one undergoes beta decay. Beta decay, there's beta minus, there's beta plus. So we need to figure out which one it is, yeah? So 231, 90. So we're gonna figure out how many neutrons, how many protons does this thorium have, yeah? I can do math on mass actually. So there's 90 protons and there's 231 divided by 90. It should be 141 neutrons. Yeah, let's check. I am right, but yes, it is 141 neutrons. Yeah, so there's no neutrons, so there's excess of neutrons. So that means we want a beta decay that increases protons, that it turns neutrons into protons to make it more even. Yeah, so we want a beta minus decay. So I think it's 0, -1 plus 231, and instead of 90 becomes wait, no, it's -1. So then you on this side, so this will be bigger. So you add one. Yeah, so 90 becomes -1 and something. So the something will be bigger than 90. So it should be 91. So it's 91, and it's uh protactinium. Yeah, that's whatever that is. And then that's the equation for the last part. And that's it for this question. It's pretty simple, but it's kind of hard as you figure out which beta decay it is, and there's 3 equations. It's kind of a lot. And now we move on to the second question. second question is on the topic of, oh my god, let me flip. It's on half-life. 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 Oh, right, two. So let's see which one it is. Here, here is a question. It says Naomi, a forensic scientist, takes a 50-gram sample of carbon from the skull of a human skeleton. She finds that the sample has a carbon-14 decay rate of 200 decays per minute. Given that the carbon from the living organism has a decay rate of 15 decays per minute, okay, part A is that it's given that the carbon of the living organism have a decay of 15 decays per minute. Decays minute. Okay, yeah, whatever. And that 14 have a half-life of 5,730 years. Estimate the age of the skeleton. Okay. So first we want to calculate. So we want the main equation, yeah. So we want to find how many actual half-life you have went through. And this is the equation, you know, we have the my goodness. Let's see, it's the we want the activity of the radioactive nuclei remaining and the initial activity of radioactive nuclei. So and then we are able to get the number of half-life elapsed. Yeah, so first we have A, which is the activity right now, and it equals to A naught, which is the initial activity, and that is timed by a half number, and the N is the number of half-life it went through. And let's see, it says 200 decays per minute. Yeah, so normally it's over, we want it in the SI unit, which is called, wait, it is called backward, I don't know, BQ, back back backrolls, and it's one disintegration per second, yeah. So it's normally in seconds, but now right now it's in minutes. But these two are dividing each other. So A naught and A will be dividing each other anyway, so the ratio should be the same. So we'll just use 200 equals, well, A naught, because it's 200, the 200 came from the 200 decays per minute, yeah? And then it's the normal rate is 15 decays per minute. And then it's in grams. But 200 decays is for 50 grams of the sample of carbon. So the A naught will be 15 times, which is 50, and times this thing. So let's find out what 200 divided by 15 times 50. And we get 0.266. A lot of sixes, a lot of seven. Okay. And that equals to a half. And normally with a good calculator, you can just calculate that normally, but we're gonna log it, because we in a log on our scientific calculators is log 10. Like it's normally log to a base of 10. So we can't do normal logs with it because we can't put in our own bases. Equals, so we log, oh my goodness. Oh, stop. What is this? Oh my gosh, can I not write over it? Remove result. Okay. So we'll log this side as well. So a half n, and then inside the log, the n can go on the outside, like over here. So then that will equal to log this thing, and then we'll divide it by log. Well, we assume it's log 10, by the way. Log 2, because n is over here instead of over here now, because that's how logs work. It will equal to n. And then we log this, so we do log answer divided by log 0.5, and we get n equals 1.90689. And then that is how many half-lives it went through. And then so the question that told us that a half-life of carbon-14 is 5,730 years. So that means years equals this thing times 5730. We get around 9 to... I'm not even close to my iPad. I don't know why it's tweaking it. Years, and that equals to 1.09 times 10 to the power of 1, 2, 3, 4 years, because physics, three things. And honestly, it should be an estimated value, so it should be in 2 decimal places, so it should be 1.1 times 10 to the power of 4 years. Same thing though, so it shouldn't be that deep. And then because part B literally asked us that why is this an estimate and not rather than a measurement, this is because that the atmosphere well, that's around 10,000 years ago is different to right now's environment, which means that the 15 decays per minute, which is given to the living bodies right now, would not be accurate to 10,000 years ago. So that 15 will have to be an estimate, making our final measurement an estimate. So decay rate of current living organism decay rate of current living organism is an estimate, and that means in the actual test or exams you should write in full sentences, but this is the main points in my opinion. Okay, this should be the main points because this is how we're testing. Decay of the living organism is an estimate, making our measure, making our result estimate, not measurement. Yeah, because skulls can go through because people burn through wood, there's bushfires, carbon things always change. So it will not always be 15 decays per minute, always 10,000 years ago. So that's why it's an estimate. But that's it for the questions. Bye bye. Maybe I'll make another video. I have to make another video of this because I have 2 more sections of this topic I haven't went through. All right, bye bye.